The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
As the title slide says, I'll be talking about the use of high-strength concrete in tall buildings, and specifically that building. Premier on Pine, downtown Seattle, corner of 9th and Pine, Seattle's theater district. The architect was Weber Thompson, very good Seattle architectural firm. The developer was Holland Partners out of Vancouver, Washington, and the contractor was Holland Construction, one of the few big developers that we work with that actually builds their own product. And does a very nice job of both. There's the shot of the 5th level amenity floor. Now notice the gray Seattle sky. We do have our share of moisture and rain in Seattle, but notice those green ferns, and that's not color enhanced. Those green ferns are the real color, so there's a flip side to that rain coin in Seattle. Some statistics. The building is 440 feet tall, 490,000 gross square feet. It's 42 stories, 10 levels of parking total, 5 below and 5 above street, and opened last November. We did design with sustainability in mind, and we achieved LEED Silver. There's the building under construction. You can see, if you look closely up at the top level, some of the formwork that was used. What we found on tall buildings in recent years is that most contractors prefer now these very well-engineered Tinker Toy handset systems. This happened to be the Titan system. There are others in the market that are equally good. Cary has a very good one. Miva has a very good one, other companies do as well. But what we found is that for high-rise buildings like Premier on Pine, that in recent years, the majority of the contractors we work with actually prefer these handset Tinker Toy engineered systems as opposed to fly forms, which gives us as designers a real advantage because we don't need to worry as much about column alignment. If you're building a building or designing a building where you're going to be building it with a table system, a fly form system, column alignment in one of the two directions is critical, because if you don't have your columns aligned, you can't fly your tables. Whereas with these handset systems, that's no longer an issue, so that if we have some columns that wander a little bit, which we did here, some, not much, but you just don't need to stress out about it as much because it has no real impact on formwork productivity. Here's the building growing up. You can see it coming out of the hole on the left and then growing up on the right. The 15,000 PSI concrete, which we did use in all of the columns, and Joe will talk in a lot more detail about that, but we did use 15,000 PSI column concrete. We started that down at the base, and that migrated downward to 8,000 PSI up at the top. Some data on the building, 7.5-inch PT flat plates throughout, highly efficient core wall seismic system. The goal in designing a concrete core, at least the way we view it, is 4 straight walls. 4 straight walls, 4 corners. Thicken the wall up to as thick as it needs to get, but try to avoid going to that 5th corner. Because if you have a 4-walled core, almost regardless of wall thickness, you typically create more efficiency and constructability. If you need to add more walls, we typically would add a baffle wall or 2 in the center, and again, keep it straight without offsets and corners. You'll see some shots of that here in a little bit. There is the Revit model of the building. We, in our office, migrated from CAD into Revit about 7 or 8 years ago now. We haven't looked back. We do all of our work now with Revit. I think some of the people in our BIM department, so-called, we used to call them the CAD department, but we changed the name a couple of years ago to the BIM department. I think they've almost forgotten how to use CAD. We're big believers in BIM, and as I say, we use Revit. We even put some of these images into our construction documents. Typically, when you open up a set of documents that we produce nowadays, the first few sheets, sometimes the first 6 or 7 or 8 sheets, will be Revit images. We'll have some overall building images like these, and then we'll have some detail images. So the contractor and the suppliers and all the tradespeople can get a real good feel of the three-dimensional nature of the building they're going to be building before they get into the detail. A quick seismic lesson for those of you that don't work on the West Coast or in seismic country. The building code essentially says if you're above 240 feet in height, or 160 feet as the case may be, depending on the torsionality of the system, that you need to focus more attention on ductility. And you have a choice of either doing that prescriptively, which means you introduce ductile frames into your core wall system, or convert from shear walls to ductile frames exclusively, or you use a performance-based design approach, which we chose to do with Premier on Pine. Joe will talk more about that, but essentially with performance-based design, since it does deviate from the prescriptive language of the building code, building officials require a peer review. The peer reviewer on this project was Joe Maffei out of San Francisco, and we worked very cooperatively with Joe over the course of, 6 or 8 months. It wasn't very long. Some of these peer reviews can drag on, but this one went very, very smoothly. And in the end, we agreed with Joe, and he agreed with us, and we went off and built the building. There's a shot of the core on the left in yellow. Again, 4 straight walls with a wraparound frame that hangs onto the core for lateral resistance, essentially. As I mentioned earlier, flat plate PT slabs all the way up with some pretty long cantilevers on 2 sides that Joe will talk about in more detail. And the 15,000 PSI column concrete, which is the primary purpose of this talk today. Now, the first bullet says we think this is the highest FC prime ever spec'd in Seattle. We're not totally sure of that. I'll probably have somebody approach me on the way out the door and challenge that statement, but we think that in the Seattle region, that's the highest FC prime ever spec'd. There has been stronger concrete produced for modulus reasons. I happen to hear just the tail end of the previous speaker, but he alluded to the fact that an ultra-high modulus will push your strength up substantially. There has been some higher strength concrete produced for that reason. We actually had a project a few years ago where we spec'd 14,000 PSI column concrete, and we were getting breaks up over 20,000 PSI pretty routinely. We had them as high as, I think, 21,000 on a 31-story tower. So we're very fortunate in Seattle to have a very abundant supply of granite aggregate. It allows us to push FC prime way up. So we do. There's no real reason not to. It's available. You can basically increase the net rentable or net sellable square footage, dropping down to the bottom of this slide. That's really the bottom line. You're trying to create more real estate in your building. And also standardize your column and wall sizes, because by standardizing those elements, you can vary the concrete strength as you go up instead of varying the element size, which improves your formwork productivity. And at this point, Joe is going to take over and talk about some more of the detail.
So right here, basically, I wanted to show an overview of the different concrete specified strengths in our documents. This table is straight from our specs, general notes, I mean. And you can see we have anywhere, the columns varies from 15,000 to 8,000 PSI. And what we do on the second column, we basically vary the strengths, and we push it as far as possible to give some flexibility to the mix designers, concrete mix subs, to kind of have a little bit of leeway. We don't usually call out 28 unless we do need 28. The core walls, see, this building was designed before the recession, and we had different concrete strengths, and then it got sold to a new developer, and they added a floor. They jammed a lot of units in it, and they got rid of columns. So that's why, part of the reason why these columns are so high is because less columns, smaller column, because the average unit size was 700 square feet. So imagine you're living in a 700 square feet as a family. So if you go 3 by 3 column, it's a bit different than 20 by 30. So on the square footage. So on the second column right here, we call out the aggregates. The elevated slabs were 8,000 and 6,000. And the reason we used 8,000 is to avoid puddling on the slabs. We have not used any puddling on the entire tower. And we used the ACI code equation. There's one that tells you that the slab and the column should be a ratio of 1.4. However, if you keep on, a lot of engineers stops at that requirement, but if you keep on reading through it, you can use 75% of the strengths of the column and 35% of the slab. So in reality, we needed about 14,000, but because of that sandwich in the slab, we used 15,000 of the column that equated to 8,000 in the slab, which is kind of a more economical approach, since the column volume, cubic yards, is much less than the slabs. So just a quick overview of the 15,000 PSI mix. We had about 775 pounds of cement, but fly ash, silica, fumes, and slag. The water to cement ratio became 0.27. It was 0.28 to begin with, and we'll kind of talk a little bit about how we went from 0.28 to 0.27 on that one. One of the biggest thing about the 15,000 that we found out on this job, different than is you can spec out 15,000, but there's a very important thing is the curing and the testing of the cylinder, because when you go to that threshold above 12,000, there's little education within the industry of how to, unless maybe you go to Walter Flood IV. And a lot of the testing lab treats these cylinders more or less, some of them, not a lot of them, like a 6,000 or 8,000 mix. So the standards of the code does not really are very stringent. There's some flexibility. The latest guide is the ACI 363 that gives some flexibility for QA, QC. So what happened on this job, the first batch of cylinders for the 15,000 mix were tested, and the way it was, basically they formed the cylinders, 4x8 cylinders, on site, they submerged them in a tank, and I think in the next day or a couple of days, they moved them in a truck to the lab and put them in a steam room in a more secure environment, and then they saw cut or ground the cylinders like the ASTM C39 tells you to do, and they didn't cap them per the standards. So what we end up, this whole thing got flagged when at 56 days, we got about 11,660 PSI on the mix, on the brakes. And usually you always go back and blame the mix designer, but you know, we had the concrete mix designer on that job had a long history in high-strength concrete. We had a lot of confidence in them. So we decided to tweak a little bit the mix first. That's why how we dropped the water-cement ratio a little bit. But then we start focusing on how these cylinders are tested and cured. This whole thing, so we got Professor Jansen, we got him to get involved in all this, and there was Jenny. So long story short, we started looking more into it and the potential reason why we're having these low brakes. And when you think about it, you know, a 4x8 cylinder, the surface to volume area is much higher than a 6x12 cylinder. So you have to be very careful with it. It's about 225% higher. So immediately after you rod the cylinders and you cap it, it has to be in a watertight environment, submerged underwater. And if it's not, even if you transport it, then it will lose some moisture. Even if you put it in the steam room, apparently, it's not as good as submerging it underwater. So what they did, the first thing they did is basically they submerged the cylinder underwater until testing. And that by itself improved the compressive strengths on these tested cylinders by 12%. And then the next thing, they started looking at the preparation of the cylinder ends. And even though the ASTM standard says you shall not put neoprene pads above 12,000, they looked into that, besides grinding and saw cutting the top to the 0.002 inch flatness. They did some qualitative studies on the neoprene pad and decided to use the 70 versus the 90 to make a difference. And then by saw cutting and using a neoprene pad, the concrete strengths went back to what the history of that mix was to begin with. And you could see here on this graph is basically plots the 15,000 PSI mix over the maturity. And the red, this is what we want to hit. And then the red was the levels below P3. And then you have level 1 on the yellow. And then up above that is the rest of the tower. And you can see as you went forward, the upper mixes start getting better concrete cylinder test results just because of the variation of little bit of variation of the curing. Maybe had to do a little bit with the change in the concrete mix a little bit, but mostly I think is curing and the way you prepare the ends. This is a summary of the 8,000 mix on the job, 12,000 and the 15,000 PSI mix. And you can see here on the average of the 15,000 was 17,108 PSI, and then the maximum broke about 18,500. The mean was 65. So we were getting way above the specified strengths that we called out on our drawings. So now how do you deal with the issue of puddling? When you have 15,000 PSI columns and then you have 8,000 slabs, that works very well when you have that sandwich of the slab right here. When it's confined on 4 sides, you don't have a problem. Then that sandwich will be about 14,000. And this is what we really needed for the strengths itself. However, some of these columns are on the edges, so that it's not confined from the 4 sides. And that sandwich needs confinement, and you need a higher strength than the slab. We don't want to introduce puddling. So what we did is we put some stay forms at the edges of the column cage, and we provided an extra cover right here, 2 inches, when they pour the slab so that the slab will sit on the column. And then it's a PT slab. We had a couple of tendons only going through that space right here. So when you pour the column, you have a gap right here. But see that we're going with these slabs about if they were pouring the slabs and the columns almost the same day, and they're stressing the third day. So it was not an issue to keep like an exposed cable in that little gap, because it's going to be a lot of times I pour the column the same day that I pour the slab. I'll show you some slides on that. So that helped quite a bit. The contractor loves it. He didn't have to puddle, and gave us what we need in that sandwich of the slab. Going on to the slab designs, it's a 7.5-inch slab, and what you see here is basically the serviceability deflection, long-term deflection on that slab. And as Cary mentioned, we had a lot of these dots right here is where the columns are, and we have a cantilever on this side, about 12 feet cantilevers, 7.5-inch slab, and same all this side right here is cantilevered quite a bit. You have a little shorter cantilever on this side. The middle piece right here is basically the core, and then on the outside you had a line load of curtain wall system coming down on the slab edge. So we did finite element modeling on all these slabs to kind of study the deflection. We monitored also deflection on the side to make sure it kind of matches what the program says. Sometimes there may be some variation. We were able to push these cantilevers to, on the diagonal, we're about 14 feet on a 7.5-inch slab. This is the layout of the slab. You know, it was interesting. This morning I was on a 318G listening to some of the discussions, and they're talking about column strip and mid strip for designing of PT. And nowadays, because of the wandering of the columns, you cannot even have a column strip anymore. You don't know where it's coming from. But you can see here how we took the PT cables, and we had to kind of sweep them around the core, catching the columns. We stubbed the anchors at the edge of the core because the core was self-climbed on the parking levels, and then it was poured floor by floor with the slabs. So on the parking levels, you didn't have any sandwich of the slab in here. On the upper levels you did, but the core itself was only 8,000 psi anyway. So these are the cantilevers. You could see some of these dimensions here. These are one of the worst on this side right here. This is a column wandering at the edge. And this column right here was 15,000 psi on the lower level. Has no, basically it's almost a corner column, and that's why we had to do this stay-foam system. This is shot below grade. We had a 10-foot thick mat foundation. The mat foundation is sitting on glacial till. It has 12,000 PSF bearing. We analyzed this building, as Cary was saying, we did a performance-based analysis. We did a time history. So we worked not only with the structural peer reviewer, Joe Maffei, it was also geotechnical peer reviewer who gave us 7 pairs of ground motion that were applied on the building, and we studied basically every 0.05 second of each earthquake ground motion, every 0.05 second of it, how the building is moving and what's the dynamics of the building and what's the nonlinearity of it. And this is how we basically check the design of that building in so many ways. Also, we did a wind test on it. We did the wind design and the prescriptive design for that matter. This is showing the foundation being poured. This was not a SCC mix. It was a high slump mix. We usually on the foundations is 10-foot thick mass concrete, but we, in our specification, will limit it was a 6,000 PSI mix, but we limited the cement to 400 pounds, and we told them to substitute this fly ash, the rest of it, so you can have a lower heat of hydration. This is the core in the middle. Interesting thing about this mat foundation, we had to pour it in 3 pours. The first pour was for the tower, right, at that eccentrically loaded tower crane. We had to underpin the building next door, and we poured almost from property line to property line. The second pour was inside the elevator pit, and the third pour was the rest of the mat. We had high-strength steel in the mat, top and bottom rebars. In some areas, you can see here that all number 11 bars, and we had about 4 inches on center on some of these bars. There's multiple layers. But it turned out to be great. They poured it in one pour, is about 5,000 cubic yard. On the core walls, and you can see now the core is coming out of the ground. Not sure if you can see this, but we had to basically increase the ductility of these core quite a bit, so we put tie steel throughout the base of the building because this is where most of the forces happen and most of the rotation actually happen, and you want to make sure you have confinement of the concrete throughout. We specify a 1/2-inch gravel because there's a lot of congestion, as you can see. They used the self-climbers on this core. You can see the outriggers here. They advanced the core in the parking. You can see how the core right here is advancing ahead of the slabs, but not too much. But then below grade, we used PT everywhere. And the way we were able to do that and to release the PT slabs from the wall is the walls were shotcreted We use shotcrete on the wall after 28 days. So you advance the whole building. You build it as if you're building from a slab on grade, and you advance the building up, and then you come back and shoot the walls. Then you lock in the slab. The slab mixes, we had a requirement for shrinkage, and they had a test for shrinkage not to be more than 0.04. And this is what I was mentioning earlier, that the minute they pour the slabs, the formwork of the columns are in place. They drop that formwork on some dobies here around it, and then they just pour the column almost the same day. The PT was, at the lower levels, it was stressed internally, and the closure pours that were created for the PT, you can see we had pockets in the banded direction, and we'll have a closure pour in the distributed direction on this side that you can't see on this shot. But were poured immediately after stressing and capping the tendon, so you didn't have to wait 28 days. So the formwork was still there below grade, and then you just pour these closure pours. Basically, that's stress leave-outs. On closure pour, since the concrete for the closure pour is locked in by the slabs on both sides, we use a more stringent shrinkage requirement down to 0.025, and we basically, a lot of times what they do is they use the same slab mix, and they add a gallon of shrinkage reducer admixture per yard. Here's some shots at the tower, looking at the slabs and how the construction of the PT, this is a core wall right here, and you can see the sweep of the tendon. One very important thing with PT is when you have a massive sweep of a banded run as such, it's critically important to not only put hairpins, like some of the standard details shows in the industry, it's also, more importantly than the hairpins, is separating the cable when the sweep occurs, so you can allow concrete in between the cables. And that becomes more important when you have a high point and the cables are sweeping, so the cables only have about an inch or an inch and a half cover on top. And if you don't have separation between the cable, a lot of times what you see is the blowout where the cable jump on top of each other, and you'll see them exposed from the concrete. This is on the upper levels, showing also how we dealt with some of the steps. This is a view of the skyline of Seattle. This building, I believe, is the building where back in the 80s, they specified a very high modulus of elasticity where the concrete strengths came close to about a little above 16,000. But the specification were modulus. The modulus on this building was not an issue because we had a core that is span to depth is about 12, at 38 by 38 foot core. So the stiffness was not as critical. Ductility was important because of seismic forces. But more importantly, compressive strength was so important for the columns. Right here, I want to show a detail right here. After some recent testing in the industry, we found out that placing the stud rails work, especially when you're in a seismic region where you have 2%, you can get up to 2% drift in the buildings. You have to make sure that you don't get punching through the columns because of that drift. And what the research showed is that putting diagonal stud rails at the corner of the column are much more efficient and will perform much better than just using the traditional four-sided stud rails on the column at the diagonals. And it turned out to be not a big issue in the field, and you'd think that would affect the placement of top and rebar and so on. Didn't make a difference. As I said, on the upper floors, the decks were poured on top of the walls. The walls will button up and then pumped. Then you stop pumping the walls after you pour the deck. So a very fast process, especially with the limits that we have in the city of Seattle. You cannot work 24 hours like some other parts of the world. You can only work, 10, I think. So they were able to get these floors, the typical floors in the building, in a 5-day cycle without overtime. A lot of these things that you see helped, This is a shot where the core was advancing this is speed ramp that goes into the parking down below grade. And you could see a lot of coupling beams in this building. We spent a lot of time. We took special attention to the design of these coupling beams. The way we designed those coupling beams is not only by the prescriptive code, but also what we did is we used the hysteresis loop on some of the diagonal coupling beam testing, and we implemented those in our performance-based analysis, which made the core much more efficient in steel quantities. This is some of the final shots on the parking level. You can see here the coupling beams. We basically had it a continuous, we had a lot of repetition in the coupling beam, so you have more of a normalized response of the core, more so than because if you have a solid, if this opening basically right here was not needed architecturally. A lot of the openings at the garage, not a lot, like you have, that doesn't go to the lobby, were actually there for structural purpose, and they were covered by either CMU or drywall. This is a building going up, and you can see here some of the cantilevers that we're talking about. Here's also some of the shots going up. This is basically almost the top level. This is a shot that Cary showed earlier where you had the beautiful deck on the outside. This one was being poured. That deck was about 10 to 12 inches thick just because of the loading. And you can see how the pump was pumping the concrete into these floors. They made this kind of interesting story on this level right about here. They're pouring the concrete, and they use the same formwork system and shoring that they did for the 7.5-inch slab. In this area right here, the thickness of the concrete was about 24 inches. They called me, and they told me this, one of the foam kind of bulged out, and they had to kind of patch it last minute. So we got a little bit of extra concrete in the beam here. It looked like a V shape. So after analyzing the beam, it turned out to have more stiffness right now because it's deeper at the midsection, so it was even better. But at the end of the day, the contractor was so nervous about it because they sell these buildings. So he took the RFI, wrote back a letter, and he put plastic on it and put it on the beam itself. So if you actually pop the ceiling in that area, you'll see an RFI letter. That's some of the views on the top of the building. This is Lake Union, north of Seattle. So all in all, the job was extremely successful. They built 51 floors in 53 weeks. And that's it.